Welcome to Monochemistry. Today we're going to look at a very important concept in terms of structure and properties of molecules, and that is called VSEPR. And I know it doesn't look at all like VSEPR, it's like VSEPR, but we pronounce it VSEPR. And here's what it stands for. It stands for valence shell electron pair repulsion. VSEPR. And that's actually a theory. So it's valence shell electron pair repulsion theory. But we don't add the T because then it would be VSEPR. Actually, I kind of like that better, VSEPR. I'll see if my colleagues in the chemistry world agree. VSEPR sounds better than VSEPR. Anyway, moving along. Valence shell electron pair repulsion theory helps us determine the shapes of molecules. So VSEPR helps us determine the shape of molecules based on the repulsion between electron pairs. Recall that, and this is a molecule, it's a structural diagram of oxygen. Okay, so it's like a Lewis dot diagram with lines indicating the bonds instead of just the dots. And it shows us two things. It shows us the lone pairs and the bonded pairs. Okay, now note, lone pairs are more free to move about than bonded pairs because this is because bonded pairs are held in place. These guys here are attracted to both of these nuclei, whereas these guys are only slightly attracted to this nuclei, and therefore they can move around more. Now, who cares, Mr. Monahan? Who cares? You should. Everybody should. But you should for sure. But seriously, because the lone pairs are more free to move about, they have stronger repulsions on each other than bonded pairs do. In actuality, lone pair to lone pair repulsions are the greatest type of repulsion you will find in a molecule. Lone pair to bonded pair repulsions are the second greatest, and bonded pair to bonded pair would be the weakest or smallest, have the smallest repulsion towards each other. It is these repulsions between the pairs of electrons that determine the overall shape of the molecule. How, you might ask? Good question. Let's see. So, you saw this picture on the first slide. And what it shows us is the shapes of different molecules based on two things. And I'm going to highlight these things for you. Okay, so the steric number. The steric number is the number of ligands, or atoms, if you prefer. The steric number is the number of atoms that are bonded to the central atom. So notice in this particular thing here, the E is always the central atom in these pictures. E is always the central atom, and the X's are the ligands, or the atoms bonded to the central atom. Chemistry terms, right? We got to sound smart, so we use these fancy things, ligands instead of bonded atoms. Anyway, you'll see quite quickly, I think, that in this case there's two. Steric number 2. In this case, 1, 2, 3. 3. In this case, 3. But wait a minute, Mr. Monahan. The steric number, you said, was bonded atoms. But guess what? It can be bonded atoms or lone pairs. So in this case, we have a central atom with 3 things attached to it. In this case, we also have a central atom with 3 things attached to it. It just so happens that the 3 things are not the same in this case. Okay, so a steric number can either be the bonded atoms, the ligands, or the lone pairs. Okay? So look at each of these examples. You shouldn't see an exception to that. Without exception, they all have the number that we're talking about here. So this one is 4. There's 1, 2, 3, 4 things attached. 1, 2, 3, 4 things attached. This one, 1, 2, 3, 4. 4 things attached. So the steric number is the combination of the bonded atoms and the lone pairs, the total. Important to note, when counting bonded pairs, a double bond and a triple bond are exactly the same as a single bond. Even though technically a double bond and a triple bond have 2 and 3 bonded pairs respectively, we treat them as if they only are 1 bonded pair. Important to note. Okay, so let's take this. What the heck is going on with this whole thing? Let's take it and let's have a look at it. So I'm going to just make this a little bit smaller here. Okay, and I am going to draw, or rather not draw because that's embarrassing. I'm just going to show you a model of a tetrahedral molecule. This is a tetrahedral molecule. Okay? Notice tetrahedral is right here. Okay? So this is like the same as CH4. Okay, if I was to draw CH4, you would see that you have a carbon in the center, and I'll use a slightly different color, hydrogens attached to it. Okay, so this is our central atom, or our X here, and these are, central atom, or our E here, and these are our X's, or things that are attached to it. In this case, the X's are all bonded atoms, or ligands. Okay, so what shape is this going to take? Well, according to VSEPR, the bonded pairs, there are no lone pairs in this, by the way. This one has no lone pairs. Sorry. No LPs. So therefore, there are 4 things bonded to it, and so therefore there are no lone pairs. So the strongest repulsion here is a bonded pair to bonded pair repulsion. So if that's all there is, those bonded pairs are going to want to be as far away from each other as possible. So in that case, I'll just blow this back up. In that case, we will go to our chart and we will say, okay, the steric number, the number of lone pairs and bonded pairs added together, is in fact 4. The number of lone pairs, steric number 4. Steric number 4, lone pairs 0. Therefore, the shape of this molecule is going to be tetrahedral. Now, tetrahedral, why would it do that? Why? Why, Mr. Monahan, why is it tetrahedral? Well, here's why. Because all of these bonded pairs want to be as far away from each other as possible. And in a 3-dimensional space, that involves making a tetrahedron. Now, a tetrahedron is a triangular-based prism. So when you draw these things, it'll look like this, right? And you'll have your, like that. Okay, so it's a triangular-based prism. I'll show you a better picture later on. Triangular-based prism. Okay, so that in that case, we have only bonded pair to bonded pair repulsions, no lone pair to lone pair, and that is the shape that it will take. Let's try another one. Here, we have a water molecule. Now, you need to, in order to draw the water molecule, you would need to add some lone pairs. Okay? Remember that the oxygen is going to have 2 lone pairs around it. 1, 2, 2 lone pairs. Okay, so the steric number of this thing has 2 bonded pairs and 2 lone pairs, and the steric number is 4. Steric number is 4. Okay, but this time, the number of lone pairs on our chart is 2. Therefore, this particular shape is going to be bent. Now, why is that? Well, here's why. Because the lone pairs want to push each other as far away from each other as they possibly can, and they're also going to have a very big impact on the bonded pairs. The bonded pair to bonded pair repulsion, i.e. this one here, is not going to be very strong compared to the lone pair repulsions. So these lone pairs get as far away from each other as they can, and that pushes these bonded pairs closer together. Okay, so those are the basics of VSEPR. Here's what I want you to do, what to bring to class. So here I have given you 3 examples. This one's tetrahedral, this one's bent, and this one is trigonal pyramidal. I want you to find, and I just got these from Wikipedia, by the way, I want you to find all of the rest of these shapes, and I want you to attach them to your notes. I want you to put them in your notes. You can either draw them, or you can actually take the pictures and you can put them in your notes, and I want you to bring that to class so I can see them and we can talk about them. That in a nutshell is VSEPR. Again, bring your questions to class.